On occasion, there are some very specific differential equations that we solve. One of them is known as the Cauchy-Euler equation. And this equation is where you still have some kind of function times your derivatives. But in this case, your function that's multiplied by is a power function itself. So you wouldn't have e to the x's or sines or anything like that. You would just have an x to the n and so forth all the way down. And so if you have this form, and there's different models that come up with this, different situations you come up with this. The a0 through an are all constants. And we're going to consider, just for the sake of easiness to look at how this works, let's consider an x squared times the second derivative of y plus a1x times the first derivative of y times a0 times y equals 0. So one other thing I want to point out with you is not only do we happen to have power functions times this, but the power on the power function is the same as the derivative we're doing. So if we have an nth derivative, we have an x to the n. If you have an n minus first derivative, you have x to the n minus first. If you have the first derivative, you have x. If you have no derivative, you have no x. So again, we're going to consider just having a second order Cauchy-Euler differential equation. Do we realize that x can't be 0? Because if x was 0, then when you divide it through by x squared, you would get undefined. So our intervals of definitions are either 0 to infinity or negative infinity to 0. We're going to consider the 0 to infinity one. Usually we're dealing with time and as that we're dealing with, or things that involve 0 to infinity. If you are going to go negative infinity to 0, then you would actually just substitute t equal to negative x. So you can still have 0 to infinity. To solve this, what we're going to do is we're going to let y equal x to the m. So we're going to think about letting y equal x to the m as my solution to this equation. And when I do that, I then have the second derivative of x to the m, which would be m times m minus 1 times x to the m minus 2. The first derivative, which would be just m x to the m minus 1, and then x to the m for y. So plugging all that in, you're going to notice that every single term, because you've got x to the m minus 2 times x squared, which gets you an x to the m. X to the m minus 1 times x gets you an x to the m. X to the 0, of course, x to the m is just, of course, x to the m. So we end up with a2 times m minus 1 plus a1 times m plus a0 equals 0, because we can divide through by the x to the m because we assumed x was not 0. So we're able to do that and get rid of that term, and we get what we called our auxiliary equation. And so if we multiply all this out, you have a2m squared minus a2m plus a1m plus a0. And then you get to solve this auxiliary equation. So this is very similar to the other different equations we're doing, but this is very specifically for this pattern of Cauchy-Euler. We also have a quadratic equation to solve. So of course you can have two distinct real roots, m1 and m2. Your y1 would be x to the m1, your y2 would be x to the m2, because we assumed that y was equal to x to the m. So y is equal to c1 times x to the m1 plus c2 times x to the m2. Very similar to the other higher order differential equations we solved. Except we assumed in those cases that y equals e to the mx. Case 2 is that you again have one real root with multiplicity 2. We'll call it m1. Your y1 would be x to the m1. Your y2 in this case, again, because you know what y1 is, you can just find y2 by using methods that we've done in the past where you know one solution, you can find the other solution. So it turns out when you do that, y2 would be x to the m1 times the natural log of x. So your y would be c1 x to the m1 plus c2 x to the m1 times the natural log of x. Your case 3 would be complex conjugate roots. So m1 would be alpha plus beta I, m2 would be alpha minus beta I. So you get c1 x to the alpha plus beta I plus c2 x to the alpha minus beta I. I don't really like x to the I, beta I. I don't like seeing an I up there in my powers. So I'm going to remind myself that x is the same as e to the natural log of x. I mean, think about it. That if you took e to the natural log of x, you would get x. So you can think of writing it that way. We just multiply the powers. So it's e to the beta I natural log of x. And we already know from Euler's formula that this is the cosine of beta natural log of x plus I sine of beta natural log of x. And x to the minus beta I, going through the exact same thing, would be cosine of minus beta natural log of x plus I sine of minus beta natural log of x. Cosine again is an even function, so it'd be cosine of beta natural log of x. Sine is an odd function, so minus I sine of beta natural log of x. And so again, y would be c1, x to the alpha plus beta I, plus c2, x to the alpha minus beta I. Most of these have an x to the alpha in them, so I'll pull that out. And you'll get c1 cosine of beta natural log of x plus I sine of beta natural log of x, plus your c2 cosine of beta natural log of x minus sine of beta natural log of x. Collecting like terms, collecting your cosine terms and your sine terms, and then replacing your constants, you get x to alpha, c1 cosine of beta natural log of x, plus c2 sine of beta natural log of x. Again, these solutions only happen if you happen to have a Cauchy-Euler equation. And that's only in very specific occasions. So let's try solving this one. This is x squared y double prime plus 7xy prime plus 5xy equals 0. Looking at that, I happen to notice that I've got an x squared times the second derivative of y, an x times the first derivative of y, and then no x times y. So this is a Cauchy-Euler. So since it is a Cauchy-Euler, I can go straight to letting y equal x to the m. So that means I will end up with the second derivative of that is m times m minus 1, x to the m minus 2 times x squared, minus 7x times m to the x to the m minus 1, plus 15x to the m equals 0. So looking at this, I'm going to get m squared minus m times x squared, x to the m, minus 7m times x to the m plus 15x to the m equals 0. And again, we assumed x was not 0, so we can just divide out the x to the m's. So we get m squared minus m minus 7m plus 15 equals 0. So that quadratic equation, our auxiliary equation, is m squared minus 8m plus 15 equals 0. We then can solve that. That factors as m minus 5 and m minus 2. So m equals 5 and m equals 3. So we get two distinct roots. So y is going to be c1, x to the 5, plus c2, x to the third. Remember, we assumed y was equal to x to the m, and we now know what m's are. So there's a solution. If you happen to have an initial value problem, you can find out what your constants are. Let's try another one. We've got x cubed y triple prime plus xy prime minus y. I do want to point out that we developed this using a second order differential equation, but this works for higher order ones. Notice this is also Cauchy-Euler because I have a third derivative times x cubed, a first derivative times x, and a no derivative with no x. So again, I'm going to let y equal x to the m. This is not as easy as just writing down the auxiliary equation as before. You actually do have to think about finding that derivative each time. The third derivative, well, we'll start with the first one. We have this equal to 0. Y is x to the m. The first derivative would be m times x to the m minus 1. The second derivative would be m times m minus 1, x to the m minus 2. So the third derivative would be x to the m minus 3, m minus 1, m minus 2 brought down, all times x cubed. So looking at this, I get m times m minus 1 times m minus 2. That would be m squared minus 3m plus 2. That's x to the m. Plus m times x to the m minus x to the m equals 0. Divide out the x to the m because it's not 0. So we've got m cubed minus 3m squared plus 2m plus m minus 1 equals 0. So we get m cubed minus 3m squared plus 3m minus 1 equals 0. So now all you do is just solve that equation, find out how that factors. That actually factors, and I would use technology to factor this. You can factor it other ways, but it factors nicely as m minus 1 cubed. So m equals 1. And so we now know we have case 2. This is multiplicity 3. So we're going to have c1 times x plus c2 times x. But again, now they're the same, so we need to multiply this by something to make them not the same. In this case, it's natural log of x. The c3 times x times the natural log of x, but now we have them the same. So what we do is we square this other one. So you just keep putting them on as many as you need until you get to your multiplicity. Okay. Let's do a couple more. Y squared times y double prime minus xy prime plus 2y equals 0. Again, this is Cauchy-Euler because you got x squared times the second derivative, x times the first, no x times no derivative. So this would be, the derivative would be m times m minus 1 times x to the m minus 2 times x squared minus m times x to the m minus 1 times x plus 2 times x to the m equals 0. Again, we were letting y equal x to the m. So now we end up with m squared minus m times x to the m minus m times x to the m plus 2 times x to the m. Everything has an x to the m to it, so we can factor out and cancel that. So we've got m squared minus m plus 2 equals 0. So m squared minus 2m plus 2 equals 0 is my auxiliary equation I get to solve. When I solve that, I end up with that m is equal to 1 plus or minus I. We have complex. We know from complex that y is going to equal x to the first because we have a real part of 1, so it's x to the first power, times c1 cosine of the natural log of x. And there's a 1 there because the imaginary part's 1 here, plus c2 times the sine of the natural log of x. All right. Okay. If you again had an initial value problem, you could solve and find out what your C1 and C2 were. Let's do one more. Let's say we have x squared y double prime minus 2xy prime plus 2y equals x to the fourth e to the x. So this one is not a homogeneous, but it is a Cauchy-Euler. It's just not a Cauchy-Euler that's homogeneous. So just as we did before, we're going to first find the solution to the associated homogeneous. So x squared y double prime minus 2xy prime plus 2y equals 0. That again is Cauchy-Euler because you got x squared times y double prime, x times y prime, and no x times y. So we again would have y equals x to the m. So the second derivative is m times m minus 1 times x to the m minus 2. The first derivative is m times x to the m minus 1. And y is just 2 to the m. Or y is x to the m. So the x to the m's will all cancel. So we can get rid of all those. We have m squared minus m minus 2m plus 2 equals 0. So we end up with m squared minus 3m plus 2 equals 0. Factor that, and it factors as m minus 2 and m minus 1 equals 0. So m equals 2 and 1. So we now know our complementary solution is c1x squared plus c2x the first. The next thing we have to do is figure out what is my function I have. And I apologize, a little bit of a thing in there. So remember, we had x squared y double prime minus 2xy prime plus 2y equals x to the fourth e to the x. The only thing is we do need to divide through by x squared to find out what my function is. So my function, f of x, is equal to my x to the fourth e to the x divided by x squared. So my function is actually x squared e to the x. That's actually what function I'm working with. We then need to find the Wronskian. We're going to find the Wronskian of our x squared and x. That would be the determinant of x squared x. The derivative of x squared is 2x. The derivative of x is 1. The Wronskian would be x squared minus 2x squared. So we get minus x squared. Well, remember, we assumed x can't be 0. So we know that this can't equal 0 because x can't be 0. So we're good with that. And so now we can then find out what that W1 is. W1 will be getting rid of the x squared 2x. That would be replaced with 0 and f of x. F of x we just found out was x squared e to the x. And then we're going to have x1. Find that determinant. You're going to have 0 minus x cubed e to the x. And then W2 is going to be, again, taking your Wronskian, which is x squared 2x. And instead of having x1, you're going to replace it with the 0 and your f of x. That derivative would be x cubed e to the x. And then you can find out what u1 prime is. U1 prime is w1 over the Wronskian. W1 we found out was minus x cubed e to the x. The Wronskian was x squared. Okay. Sorry, it's minus x squared. So we get that this is x e to the x is what u1 prime is. When you take the derivative of that, you find out u1 is equal to x minus 1 e to the x. And u2 prime is w2 over w. W2 was x cubed over e to the x. The Wronskian was minus x squared. So it's minus x e to the x. I'm sorry, minus x. Oops. Oh, I apologize. This is x to the fourth. Because x squared times x squared is x to the fourth. So this will be x squared e to the x. Sorry, that's still 4. All right, so then u2 is going to equal finding the integral of that, and the integral of that turns out to be minus x squared minus 2x plus 2 e to the x. And so we now know that y is our complementary solution, which was c1 x squared plus c2 x plus the y1, which is x squared times u1, which was x minus 1 e to the x, plus y2, which was x, times u2, which is minus. So I'm going to change this to a minus. X squared minus 2x plus 2 e to the x. And there is your solution to this differential equation. And you can multiply the x through if you want to and make it a little bit nicer and prettier looking. In fact, you notice you have e to the x's in a bunch of places, so you can multiply everything together, collect like terms, and you get that y is equal to c1x squared plus c2x. We have an x cubed minus an x cubed, so that will cancel. We have an x minus x squared e to the x minus, so we have a minus x squared e to the x. And a minus x, another minus x, 2x, wow, a plus 2x squared, so that actually becomes plus x squared e to the x, and then minus 2x e to the x. And there's your solution to that differential equation. And so that's how we deal with the Cauchy-Euler. It looks very similar to other things we've been doing, it just changes a little bit because of the substitution.